Thank you everybody for being there. I'm Nicolas Kowalski. And we're going to present some of our work that we did in the past year on how we optimized our TensorFlow models for inference to get a 10x speed up, on which actually targets under 5 milliseconds. So I'm going to start describing quickly Criteo. We're an online advertising company that's trying to show the right ad to the right person at the right time. We're doing our best to make advertising more relevant and less obnoxious. And we're actually a company that not a lot of persons have heard of, but we have most likely interacted with a lot of you in this room on a daily basis. We have petabytes of logs, and we're seeing 500 billion events every day. We're dealing with millions of predictions per second, and we're interacting overall with 1.4 billion internet users. So we have 35,000 servers in 7 data centers that are all built and operated internally at Criteo. And we're seeing up to 4.1 million requests per second. And our services are actually operated with 99.95% availability. So we're truly a big data company.
So both of us are from the what we call the prediction team, and the prediction team basically at Criteo is in charge of building the machine learning platform for Criteo. So our clients are internal users building the models, and we help them, providing them tools and how to solve the models, how to test them, and so on. So we are not a new company, and so we have a bit of legacy. And our legacy is twofold. First, in how we do the models that we used, and we've built. So we've been using logistic regression throughout the years. We've been milking logistic regression. The reason for this is that it's a very simple model. So we're not in the deep models that most of you will probably be talking about here, but. So since the model is very simple model, it means that all the magic happens before. So it means that we have a lot of pre-processing, and so we compensate the simplicity of the model by using crosses, combining dimensions together to add a bit more power to the models. The model is quite fast to predict with. And also, what we have in our legacy, the second part is the tech part that we have. And the tech part is, for historical reason, Criteo has lots of in-house C# homebrewed libraries, and the prediction libraries and our machine learning libraries, another one of them. So we have C# with logistic regression, and that's our starting point. And we also have our own Hadoop servers, so we bind C# to Hadoop and Spark using some Java. So we have this kind of a fancy mix of C#, Java, Spark, Scala, and so on. And somehow we're doing machine learning with this. And it's been somehow successful. Obviously, the world has changed, and we want to upgrade our machine learning platform. And one of our tasks is to open it and to add new technologies, and obviously TensorFlow is one of it. Because we want to go to deeper models and surf the deep learning wave to see how it goes. So what we'll be presenting here is basically how we took our naive logistic regression model and tried to implement it in TensorFlow, and try to, within the constraint that we have, which is online serving.
So the rest of the presentation will go as follows. First, we're going to describe the problems that we have and the constraints that are very particular that we have. Then we're going to share some awful initial results and common optimizations that did not work out so well, spoiler alert. Then we're going to describe how we profiled our model and how we optimized it using low-level APIs. And finally, we're going to conclude and open up for future work. So most of what we're doing at Criteo happens in real-time bidding. When a visitor enters a web page, there are going to be ad spots, and an ad server is going to open bids for those ad spots for supply-side platforms, such as Criteo's and others, to bid. We are then going to try to predict what is the expected value for us for this ad spot for this customer. And we're going to provide a bid according to this value. And then the ad server is going to select the highest bidder and serve the ad. The thing is, between the time where we're aware of the bidding process opening and when we need to actually provide our bid, we have about 50 milliseconds. Now, during those 50 milliseconds, we're going to actually have 10 to 100 predictions performed in parallel because we're going to try several possible products that we would want to display. We want to have several configurations. And all this means that at most we're going to have 5 milliseconds to actually perform an inference on our online model. And our legacy engine is actually able to preprocess and do the logistic regression in 0.5 milliseconds. So it is incredibly fast compared to a lot of what other users of TensorFlow are used to. Actually, our total limit is actually kind of the noise of a lot of other models. So as we said, we have a pretty involved preprocessing where all the smartness of the model is expressed. What we're doing is that we are taking 50 to 100 input features, and we're going to convert them all to categorical features using bucketization if needed. Then we're going to add 100 to 200 crosses of those features. And what that means is that we're going to have about 200 total features. Some of them are crossed. So we're going to have a very, very huge space that is very sparse. And we actually have a space that is too big to be treated. So we're going to reduce the dimensionality by using hashing. We're going to actually hash all of those features into a single hashing space of dimension about 100 million. Now, one thing that people think about when they think about improving online inference timing is to use hardware acceleration. That's not an option for us because, as said, we have about 100 million weights that are in a very sparse user context. What we need to be able to do is efficient dense.sparse vector multiplication. And the GPUs are actually not offering any speed up on our models.
So we started our work 9 months ago, or something like that. So at the time we started with TensorFlow 1.12, so it dates a bit, and we used the estimator API. So the starting point was to really re-implement the thing that we know, which is the logistic regression model, using TensorFlow. Not that it's a final destination, it's just a starting point. We know it very well, and we will be able to compare it, and probably open to some smarter models like wide and deep and so on. So it's just a point, it's just a way to compare our models. So our technical stack, again, is in C#, meaning that all our front-running servers are running C# VMs, and our prediction library is written in C# and it happens inside these C# VMs. So it means that somehow we have to inject, to be able to inject TensorFlow into this. So when you want to do online serving, the natural way to do it, at least, I mean, it sounds very natural, is to use the server provided by Google, which is TF serving, which has lots of good niceties. You can expect from Google to have implemented a very efficient server, and obviously it is. From the architectural point of view, it totally makes sense to decouple our business logic, to keep it in C# and to have another component which will be focusing on the predictions and on the models. The server comes with batching on the server side, meaning that we don't have to do anything. We can just send single predictions, and the server will batch them efficiently. So this is also very nice. But we were a bit worried about the additional delays due to the network, and also about that we had to refactor our code to be able to inject this. So this was plan A, and in parallel we had a second plan, which is plan B, to do TensorFlow within the C# VM. So we had this in-process track B, where basically we're calling TensorFlow using C# to TensorFlow binding, which has been developed by somebody from Microsoft, I think, which is called TensorFlow Sharp. So track B is doing TensorFlow inside the C# VM.
All right, so the initial results were actually really, really poor. Our inference was about 30 milliseconds per prediction. And as said, we were doing in less than 0.5 milliseconds with our legacy engine. So we had almost an 100x slowdown. And most importantly, that was way above the 5 milliseconds limits that we had, which meant that if this was the limit of TensorFlow, TensorFlow was not an option for us to use online, which was very disturbing. Now, there were some good news. First of all, the cost of remote prediction, that was a concern that we had, as said, for using TF serving, but actually it was low-ish. It was under 1 milliseconds. So it was not negligible completely, but it was really low in front of the prediction itself. And the other good point was that batching was extremely efficient and extremely easy to use in the TensorFlow serving setting. With just a command option, we were able to get 5 to 10x throughput at almost no latency cost. So what that meant is that if we solved the latency issue, then we pretty much were golden. All right, so how do we solve that? Well, we looked up online on Google, as most of us do. And at the time, what we found was actually a comprehensive tutorial on Medium by Lukman Ramsey that described several methods that were optimizing the inference online. So what he was proposing was to, first of all, freeze your model. So you're taking all the nodes that were variables during your training, and you convert them to constants. Then you're going to prune, so you're going to remove all the nodes, such as batch normalization or stuff like this, that's only necessary for training, and you remove them for serving. Then you have constant folding. So you're going to actually take all the constants that are identical and put them as a single node in your model. Then there were two other optimizations, folding batch norms. Okay, so this was not something that we were really interested in because we were our main target was logistic regression, so that was not really a concern for us. And the other was quantization, but that has an impact on the machine learning performance of the model, so we didn't want to go down that road. There was a small catch in the blog post in that actually the freezing was taking your saved model in TensorFlow, converting it to a graph model, which is a less rich version of it. And so you needed to convert back your graph def into a saved model. And it seemed easy, but it was actually quite complex. There was a lot of meta information that you needed to track from your initial model and then somehow provide it back into your final model. The good part is that actually we learned a lot about how TensorFlow graph was functioning, which is that you have this intermediate representation of your program, and you can really manipulate it in a very powerful way. You can enrich the node, you can add metadata information, you can directly cut and paste nodes from another graph directly into your graph, and all that was not obvious when we started this exercise. So we learned a lot. The bad part was that at the end, it was quite a lengthy process, and we had literally zero improvement to show for it. And in hindsight, it actually makes sense. All that we described, freezing, pruning, most of this is actually improving your model for inference, but by improving it in terms of the size that it is taking. You're removing nodes, you're reducing the size of your model, which is very useful if you're going to target Android devices or web browsers. But in our context, we are on huge Hadoop servers. We have a lot of space. That's not a concern for us. And there was very little, and in our case, no improvement in terms of the latency itself.
Okay, so applying the medium post didn't work. So the next usual suspects when you try to optimize for latency and you search in Stack Overflow is you use XLA. That's the next one you want to use. So XLA, disclaimers, we're not experts in this. So this is our, what we understood of it. And probably you have guys from Google who can give you all the good details of how it works. So this is our naive vision of how it works and how it should behave. So just to understand what XLA does, first we need to draft roughly what a TensorFlow executor is. So you can think if your graph is a program, then the TensorFlow executor is really the interpreter of your program, and XLA is the compiler. So one of the key things that you might want to so if you look at what the executor does, the executor has a job of scheduling all the operations that you have to do, placing them on the right devices so that you correctly use all the resources efficiently, and none of this is very trivial. What I'm trying to get at is that each operation that you have in your graph has an inherent cost tied to scheduling and all of that, and probably you want to get rid of that. And that's exactly what XLA does. So this is, again, our naive understanding of XLA. So you have this magic wand. So basically, you have your graph, and you have, for example, a set of operations. So you have a dot product here, and then you add another tensor, and then you apply some math on it, math function. And if you leave it like that, what the executor will do is we'll have to schedule all the three operations. And so you have the overhead. Probably you're trashing the cache lines of your CPU or your GPU, so this is not efficient. So what you want to do is probably you want to bundle them together into one big kernel and to be efficient. And that's probably what XLA does. And basically, in a way, XLA is kind of building a SIMD pipeline of your operations to make computing efficient. So that's one of the first thing. A second thing, which is totally tied to that, is probably memory streaming. So memory streaming, if you look at the design of TensorFlow, basically each operation is a pure function, meaning that it has no side effects. So it means that basically, if you have a naive implementation of that, of an executor, you're copying data over and over and over again. Probably the standard executor doesn't do that, but probably it does. For example, it means that if we go back to our example, the dot product here basically will take two inputs, W and X, and will materialize the full result before sending it to the add operation, and then the add operation will also materialize the full result set before sending it to log, and obviously this is not efficient. So what XLA does, it builds an efficient memory pipeline tailored for your architecture to really take advantage of your SIMD architecture. So you won't have this intermediate copies, you will have an efficient batch size of what your architecture will be using. So this is, again, very efficient, and we want to leverage this. So this looks very clean. XLA has, if I'm not mistaken, it has LLVM inside it, so meaning this piece of software is able to produce code targeted for your special architecture. Which is obviously what you want to get the most of it. So, to our knowledge, there are two ways to activate XLA. The first one is ahead of time compilation. What it does is basically it's a command line, and you feed your graph to the command line, and what you get in return is you get a Linux shared library with a C header that you can then link to your program. So basically, using this, the graph totally disappears, and turns into a nice shared library. So this is very neat, but in our architecture, it doesn't fit very well because we want our users to be able to build models without having a complex tool chain. So there is a second way to activate XLA, which is just-in-time compilation. And this is the path that we followed. And basically, just-in-time compilation does the same, except that the shared library is produced in memory, and you directly link to it. So this is the path we followed. Now, XLA was a bit experimental at the time that we used it. So CPUs were not supported very well, and some operations were not supported at all. So for example, string operations, asset lookup operations, and so on were not supported, meaning that if we fed our full graph to XLA, it wouldn't work. Basically, it wouldn't compile. So, but using the nice trick that we had before, which is we were now able to manipulate directly the nodes of the graph, the protobuf nodes of the graph, we were able to totally rebuild the graph in the way we wanted. So what we did is basically we opened the protobuf nodes and we visited the graph to identify the subparts which were compatible with XLA, and we decorated these subgraphs with the XLA JIT operation, and ta-da, it was working. So we were happy until we measured, and we didn't get any latency improvement. We got 0. So we were a bit disappointed.
Yeah, so at this time, so we had spent quite a bit of time trying to improve our models. We had nothing to show for it. We were a bit worried in front of our boss during meetings. But thankfully, we actually had contacts directly with the TensorFlow team, and they provided a lot of useful tips and insights. And one of the things they mentioned was an experimental executor that was targeted towards single-threaded execution. So as said, the standard executor does a lot of scheduling with a queue where you pop and push all your operations. But in our case, we have very, very small operations that are atomic, that don't do a lot of things. And so the overhead of scheduling them can actually dominate in front of what they are actually doing. On top of that, as said, we are already dealing with parallelism at a higher level. We're doing 10 to 100 prediction in parallel. So it doesn't really make sense to do also parallelization at this level, especially since we're targeting 1 or less milliseconds. So this should all be very quick. And indeed, by activating this experimental executor, we are able to see some nice improvements of 10%, which is not nothing. But that still left us quite far off from our target. And we had spent like about a month at this point, both of us, trying to improve our model. But what we realized at this point is that we had gone at the problem the wrong way. We just tried to look up online for generic solution to our problem, but we had very specific constraints. And what we should have done from the start is actually try to profile our program. So that's what we did next. So we looked up online how to profile a computer program. And we found 5 or 6 different options that were a lot of the time quite complex to just set up. Some of them required still to use Basel compilation, for example. But at the core of them, we realized that by digging a bit, all of them were actually relying on the same exact object, a run metadata object that was returned by your session.run. And this object contained all the time and space consumption information for each of the operations executed by your graph. The easiest that we found was just to cast this as a Panda data frame and manipulate it with some very simple small Python functions using namespaces that were intelligently designed to group our operations together. So we were able to actually have very efficient profiling doing that, if not pretty. And what we realized is that actually most of our time was spent doing some form of casting, reshaping, slicing tensors, so just manipulating them and not doing much. That was very surprising. We were expecting that maybe we completely missed something obvious and we had one very big operation that was taking all the time. But actually, what we had was just a lot of operations that were all taking pretty much just overhead. But at this point, we had no idea how to improve that.
Okay, so we're in a situation where we have a program, we've profiled it, nothing's obvious with the profiler, so then you do the next step, which is you look at the assembly code. And in TensorFlow, when you look at the assembly code, basically you look at the low-level operations that have been generated by your high-level API. So that's what we did. We opened TensorBoard, we looked at the graph, and we looked at the nodes. And the first thing which stood out was the number of operations we had. So the graph had something like 10,000 operations for 200 features. That's a lot. And if you do the math, basically you have you end up, so if you have 30 milliseconds for inference, it means that you have 3 microseconds per operation, and somehow it sounds okay. I mean, you kind of understand why the thing is slow. We have too many operations. So we were trying to understand that. Normally, our graph should be very simple. Again, we're doing logistic regression. We're not using any fancy model. So the graph should really look like that, meaning that we have a bunch of feature messaging at the beginning of the graph, bucketization, cross, and then you have basically the core of the logistic regression is a simple dot product. That's all. You have a dot product, and then you have your activation function, the sigmoid, and that's it. So it should be a very, very small graph. So we are trying to understand if we could find this pattern in the graph that was produced. And we were looking mainly for the dot product. The dot product should have been very easy to spot, but it was not. I mean, we were not able to find the dot product. So basically, we're in a situation where profiling got us nowhere. We looked at the assembly, we looked at the graph, and we were not even able to find the dot product in the graph, so we were a bit stuck. So we decided to go one level deeper, which is to re-implement the model using low-level operations, just to understand how it was working and to see where we missed something. So the first step when you do this, I mean, for our model, was really to, so the sigmoid function, this was easy to find. And so we were really looking for this dot product function. So in our situation, the dot product is a dot product, the little twist here is that it's a dot product between a sparse tensor and a dense tensor. So we have dense weights, which are the weights which have been learned by the model, and we have sparse tensor input, which corresponds to all the input features. So we are looking for just this simple operation. So if you do this, and if you, so we opened the library and we looked for this operation, and we found several alternatives. So you have matmul. The second one is less obvious. You have the embedding lookup sparse, and so on and so on. So we're trying to understand which one we should be using. And we looked at the documentation, and the documentation was not so obvious. They had subtle differences between all of them. And at this point, by looking at that, we understood something which is fairly important, which is, in fact, totally obvious, but which is hidden when you use a high-level API, which is that all operations, basically, are dealing with either dense tensor or sparse tensors. And if you use if you use a dense tensor operation where you should be using a sparse tensor operation, basically your program will blow up. So it will be slow, and or you will blow up in memory. So this is obvious when you look at the low-level operations, but it's not obvious when you use your the estimator API, basically. And probably one way to spot this is probably to look at your graph and to look at the shapes you have in your graph. And probably if you've messed up something like that, you might have some silly shape in somewhere in your graph. Now, the other thing which is even less obvious is that one of the niceties of TensorFlow is that each operation is different. You get the gradients of each operation. And again, the gradient is a tensor, and the gradient can be sparse or dense. And this is not really advertised. And to check this, you need to test it in Python, and just to pretty print it and to see if it's dense or sparse. And if you mess this up, then the same problem will happen, but not at inference time, but at training time this time. So what we did in the end is basically, we used none of the above operations. We just implemented a cheap dot product, which is 2 operations. We used gather and reduce sum, and ta-da! With 2 operations, we had a dot product, and it was very, very efficient. And by doing this, in fact, we even found one of the culprits of what was producing such a mess in our graph, and this was this TF unbending lookup sparse, which was, in our situation, producing way too many operations, in fact. So this was one of the culprits of why we had so many reshapes and all the tensor messaging. So this was a first significant step towards our success.
So while looking at our model, trying to re-implement it with low-level APIs, another thing that we noticed is that we should actually stack operations together by type. When you use feature column APIs, the naive way to do it and the way it is done is actually you have a bunch of features as inputs, and you're going to have each of them have its own silo of preprocessing and of operations. And they are going to be done all in their own separate way. But in our case, we have a lot of features. We have 200 of them, and a lot of them are actually following the same pipeline of preprocessing. So that's actually a huge waste. And what we want to do is, early on, find all the tensors that can be grouped together by shape and by type, put them together in a tensor of a higher order, and just feed that in the preprocessing pipeline and mutualize all the preprocessing nodes. By doing that, we are actually able to reduce drastically the number of nodes in our graph and to take advantage of TensorFlow strong suits and really, instead of attacking it in an orthogonal way, to really go along where the TensorFlow is trying to optimize, which is to take, to vectorize all your information and to take big tensors of operations.
So the next thing we tackled was hashing. So using this neat trick of stacking operations together to use the SIMD capabilities of TensorFlow. So we looked at how we could do hashing using the TensorFlow library, and basically the library, the only thing we found was a hash function where the input were string tensors. Okay, so string tensors. So and we understood that the high-level API was, and in fact our input was mainly integers, doubles, and not so much strings. So what the high-level API was doing, it was converting all our integers and doubles into strings, but by string I mean printing them and then hashing them into integers. So we re-implemented that. So we re-implemented using low-level operations an equivalent of murmur 3. And using the technique of stacking all operations together. So now we had a hashing function which was able to hash all the input in one set of operations. So we reduced the graph very significantly. And once you have hashing, then it's very, very easy to have crosses. Basically, if you have your hashed indices, the only thing you need to do is somehow combine them using some binary operation, and tada, you've got crosses for free. So now we have crosses in one single operation. So in the end, this produced a graph which was, in fact, producing good results. So we were now, with this new graph, we were at 3 milliseconds instead of 30 milliseconds. So that's a 10x improvement. So this is good, we are happy, we can put this online, it's good. But if we try to take this graph now and compile it with XLA, it still doesn't provide any improvements. So maybe we messed something with XLA, and we still have 10x lost somewhere. I mean, our naive implementation of the same stuff in C# is performing in 0.3 milliseconds. So the next step for us will be, and this is something we haven't done yet, is probably to go one step deeper again and probably have a look at the executor and try to understand how it's working.
All right, just to conclude quickly. So mostly we wanted to share what we learned because there was a lot of painful lessons along the way. One of the main lessons that we had was that the graph was an intermediate representation of your program, and that you could really manipulate it in a powerful way. We dug quite deep into how we could profile our program and use TensorBoard to understand what was happening. But I think that the main takeaway is that the estimator API and high-level APIs overall hide complexity, which is something that is desirable when you're trying to prototype something. But then when you have constraints that are a bit specific and not the most used cases, you're going to actually have the high-level API hide stuff that you want to see. And we should not have been that afraid of going directly to low-level operation and to try to look directly at what was happening. And to open up just so in the next quarter, we have planned to migrate to TF 2.0 now that it is a stable release. And one of the things that we are really hopeful for is that Keras seems, on paper at least, we have not tried it yet, but it seems like it's going to play much more nicely with trying to interweave high-level APIs and low-level APIs. And that's something that Estimator API was not playing nice with at all. We ended up just scratching everything from Estimator API, feature columns, everything, and just converting to an Estimator API just at the end to be able to serve it online. So yeah, that's our big hope for the future. Thank you.
Thank you.
Do you have any questions for us? Yes.
Maybe slightly off target, definitely I'm not trying to get you to disclose your secret sauce, but are the 200 features that you have available to at inference time, are they just properties of the device, or do you have any sort of like lookups? If you're doing personalization, you could be storing data on the user in the model. Are you doing any of that, or is it just from what you have available at device?
So the question is, are we just using information on the device, or are we doing, are we doing lookup? So do you want to take this one?
Yes, sure. So yeah, it's the second option. I mean, it's not only devices, it's all the information related to the context. So it's going to be past events, the context, the web page, products, and stuff like that. There is. Okay, there is. Yes, there is. And we have lookups in memcache, for example. So we have a memcache in our architecture. Yeah.
Okay.
One last question.
Okay.
You're in production with this, and if so, does your use of XLA impact how you roll out?
So we are not yet in production because we have other issues with how on the machine learning performance of the model. Basically, we're not yet able to perform as well as our in-house model. So we're dealing with this first. Yeah.
Thank you.